Greetings to everyone. My name is Branislav and I will show you and present you the paper with the subject that you can see on the screen. It is the fracture behavior of reactor steel 20MnMoNi 55 in the transition temperature region. So let's start. In this study, the effects that have an influence on the cleavage fracture toughness are considered. It is known with crack influences, a low temperature contributes to the fracture to be more faster and have an impact on the fracture mechanics parameters values, as well as on the fact that the fracture is more likely to occur due to cleavage. This aforementioned is discussed by analyzing the parameters that you can see on the slide to be more accurate their scatter by testing of CT50 specimens in the transition temperature region at -60 and -90 degrees of Celsius. Some of the previous results were added in this study, which will be presented in the further part of this lecture. A topic of numerous studies over the years involves the extent of working conditions necessary to change the nature of fracture from ductile to brittle and vice versa. In general, this change depends on the material properties. In our case, for steel 20MnMoNi 55, which shows its dependence and general sensitivity to temperature changes. As it is well known, plane stress and plane strain state define plastic and brittle fracture. Under plane strain, fracture is brittle. One of the ways of achieving plane strain state in specimen is to take into account specimen thickness. The larger specimen have an influence that fracture is more likely to be brittle, as reflected on the relevant measured fracture parameters. In standard tests carried out for the purposes of determining basic mechanical properties, as well as fracture mechanic parameters, there are two distinctive techniques for defining the loads during testing. The displacement rate for a given specimen can be defined by changing the load over time, and in this case the force increment have a constant value, or changing the deformation over time, and in this case the deformation increment have a constant value. Depending on the testing rate, metals can be divided into those not sensitive to it or those whose mechanical properties change with this rate. Numerous studies over time have confirmed that in the case of ferritic steel, the change in temperature also results in the change of mechanical properties, wherein the toughness decreases, and along with it so do the fracture mechanics parameters. Toughness of steels and alloys meant for a low temperature exploitation are typically defined by their transition temperature requirements, and it was experimentally determined that such materials exhibit ductile fracture at higher temperature and brittle fracture at lower ones. The testing of the CT50 specimens made of previous mentioned steel were carried out on the two temperatures at it is mentioned before. Total 11 specimens with B net 16 millimeters and 2 millimeter side grooves on the both sides were tested in the first set of testing on the minus 60 degrees of Celsius. This first set of specimens were tested with displacement rates 0.5 and 0.02 millimeters per minute. 16 specimens with B net 20 millimeters and 2.5 millimeter side grooves on the both sides were tested on the minus 19 degrees, and displacement rate was 0.5 millimeters per minute. According to material properties, obtained values of strain diagram and the matrix showed on the slide, the relevant fracture mechanics parameter obtained by testing of previous mentioned CT50 specimens was J integral at the moment of a cleavage fracture, or just simply JC. It should be emphasized that this study relies on the Heron's work, and other relevant parameters introduced by him were discussed as well, such as the distance between the fatigue crack tip and the cleavage initiation, or just simply RC. Beside that, ZC, which represents the distance of RC from a medium line of the specimen thickness, were analyzed, as well as their dependence. On the left table are shown the values of JC as well as RC and ZC for specimens tested at minus 60 degrees of Celsius. As is shown, displacement rates during testing were given for each specimen, and the JC values are given in the ascending order, which follow RC values. And on the table on the right side are shown the values of JC as well as our values RC for specimens tested at minus 90 degrees of Celsius. And to see a bigger picture on the other effects, the results from previous set of testing are given here. The results of JC by testing of CT50 specimens at minus 60 degrees of Celsius with specimen geometry B net 20 millimeters and side grooves of 2.5 millimeters on each side. On the table are given JC values only, because this parameter will be discussed as well. Based on the obtained results, obtained JC values, it can be observed scatter to be more greater with temperature increasing, as can be seen in the on the diagram. As well, with temperature influence on the JC values, it can be observed the influence of the specimen thickness on the JC values as well. So in the next slide, we put JC values from previous mentioned series of testing CT50 specimen at minus 60 degrees of Celsius with B net of 20 millimeters along with B net of 16 millimeters. And from this diagram can be observed that values of JC are a bit lower in comparison to series with B net 16 millimeters. This could be contributed to, how to say, more plain strain state, which lead to more faster fracture of CT specimens. So it looks like this gives more the conservative data, but still there are severe scatter of the results, and to be more accurate, scatter of JC values. Influence of the temperature on the RC-JC dependence can be observed and seen on the left diagram. The blue dots have a higher values than red ones and can be observed some form of linear distribution. As for the red dots, no distribution can be observed. Scatter of RC are greater and it behave in non-uniform manner in comparison to blue ones. On the right side, dependence RC and JC can be observed. For the CT50 specimens tested at minus 60 Celsius degrees, and the idea here was to show the influence of displacement rates on the cleavage initiation sites. Scatter is obvious, along with scatter of JC. From this small number of results, can be observed that greater displacement rate during testing provide cleavage initiation to be on the middle of the specimen, but yet more results need to confirm this statement. The few observation could be emphasized. The scatter of JC parameters are larger with temperature increasing, which can be seen from direct comparison of JC values. The scatter of JC is larger with specimen thickness increasing, but it have not been seen from the results of testing of CT50 specimen with B net of 16 and 20 millimeters. The only thing that could be said is that the thicker specimen gave more conservative results, but yet scatter are also large in a very broad range. Scatter of RC as well as its value is also larger with temperature increasing, and the effect of displacement rates on the cleavage fracture require more testing and experimental results.